So hopefully when we talked about speed, we didn't confuse you too much. Hopefully everything is all good there and you've got your quizzes figured out. Now we're going to talk about acceleration. So acceleration is just the change in velocity. Now I remember before I said the word velocity is like using the word speed. Okay, so we can use those. We can for my class, you can use them the same. But if you do another physics course, they won't be quite the same. So it's the change in speed per unit time. So acceleration is the change in velocity or the change in speed per unit time. I've left the word velocity because this graphic, which is a really nice graphic, uses v. So velocity is speed, and whenever we do acceleration, we're going to do acceleration in meters per second. Meters per second squared. So speed has to be in meters per second. Time is going to be in seconds, and acceleration is going to be in meters per second squared. So you may occasionally have to do a conversion from kilometers per hour to meters per second. Now, why is acceleration always measured in meters per second squared and not in kilometers per hour squared? Well, there's a couple reasons for that. Think about when you're driving and you accelerate. Do you accelerate for a long time, or do you accelerate for a short spell and then do a constant speed? Most of us are accelerating for a short time and then holding speed, or we're decelerating, we're braking for a short time. Because we're doing this over short periods of time that are just several seconds, it doesn't make sense to measure that time difference in hours. So because we accelerate over short periods of time and our acceleration happens over short distances, we use meters per second instead of kilometers per hour. When we're just traveling without accelerating, then we use our kilometers per hour because we're traveling at the same speed for a long time, for a long distance. So that's just a simple thinking about how big the numbers are. It would be awfully strange if I said I was going to visit my parents and you guys would look at me like I was nuts if I said, yeah, it's about 452,000 meters away. You'd say, what are you talking about? But if I said 452 kilometers is my trip, you might be able to put that into some perspective. All right, we're going to start out with some calculations. The calculations are nice and easy. So the equation for acceleration is equal to the change in speed or the change in velocity divided by time. So here we have a car accelerating from 0 to 27 meters per second. That's 60 miles per hour, and they're doing that over 12.7 seconds. What is the acceleration of the vehicle? So first of all, we need to find out what is this change in speed? Well, they're going from 0 to 27. So the change is 27 meters per second. So the change in velocity is 27 minus 0, which is just 27. So we can put that into our equation. The change in speed is 27 meters per second. The time I'm doing that over is 12.7 seconds. So that gives me an acceleration, if we put that into our calculator, of 2.1 meters per second squared. Acceleration always has that second squared. Example 2. The average vehicle is capable of a maximum acceleration of 3.7 meters per second squared. A car is traveling at 22 meters per second and then it accelerates for 5 seconds. What's the change in velocity? And then I want to know what's the speed, what speed is the car actually at? And then we're going to figure out what would it be if we had to switch it to kilometers per hour. So A, what's the change in velocity? Well, our equation says acceleration is equal to the change in velocity divided by time. We know that our acceleration was 3.7, and our change in velocity is what we're looking for, divided by 5 seconds. I want to get rid of the 5 seconds, so I'm going to multiply both sides by 5 seconds. They cancel, and our change in velocity is equal to 5 seconds times 3.7, which leaves us with 18.5 meters per second. That's my change in velocity. B, what speed is the car now traveling? Well, I started out at 22, I accelerated, so I sped up. by 18.5 meters per second. So 22 meters per second plus 18.5 meters per second, excuse me, leaves me with 40.5 meters per second. All right, if 1 kilometer an hour is 0.27 meters per second, is the car speeding if it passed in a 90 kilometer an hour zone? So if I'm accelerating to pass a car, am I speeding if it's a 90 zone? Well, let's figure it out. So we know we're going 40.5 meters per second. 1 kilometer an hour is 0.27 meters per second. So 0.271 kilometer per hour. So it's 40 divided by 0.27, and that leaves us with 150 kilometers per hour, major speed. So we're definitely speeding. Now here's something for you to think about. My sister has a bit of a heavy foot. She has a tendency to get caught for speeding. And one day she got pulled over in Toronto, and the police officer gave her a stunt ticket for accelerating too quickly. Now I want you to stop and think for a second. That's the version she told us anyway. Is the problem going to be accelerating too fast? Or is the problem going to be accelerating for too long? Which matters? Well, if I accelerate very quickly for a short time, but I stay under the speed limit, is that a problem? No, it's not going to be an issue. But if I have a large acceleration and I do it for a long time, more than 5 seconds, or maybe just the 5 seconds, is it going to be a problem then? Yes, it's going to be a major problem then. So for her particular situation, I'm not sure it would have been a good idea to talk back, but she could have challenged the police officer and said, "Sir, I'm sorry, but the issue is not how fast I was accelerating or how large my acceleration was. The issue was I accelerating too long, and did that put me over the speed limit?" I don't know. I didn't think there was a law against how fast you could take off. Peeling tires is not always a good move. Anyway, her stunt driving ticket definitely made issues for trying to get insurance for quite a long time. So try not to accelerate too quickly if that is an acceptable thing to be charged for. Now, I made an error here, and I have the same question twice. So we're going to skip the second example 3. We're going to jump to example 4. So in example 4, we have the average vehicle is capable of a maximum braking deceleration. So deceleration means we're slowing down. Braking should imply we're slowing down, of 4.5 meters per second squared. If a vehicle is traveling 32 meters per second, so approximately 115 kilometers per hour, how long will it take the vehicle to come to a stop? Okay, so let's figure out our pieces. We're slowing down, so our acceleration or deceleration, I didn't mean to put a bracket around that. So our acceleration is equal to 4.5 meters per second squared. Initially, I'm traveling at 32 meters per second, and I'm coming to a stop. If I start at 32 and I come to a dead stop and have 0 meters per second for my speed, then my change in speed is 32 meters per second. Okay, and I want to know how long is it taking to stop. Easy calculation. Acceleration is equal to the change in velocity divided by time. You can use your triangle to rearrange if you want. We're going to find time equals the change in velocity divided by the acceleration. Time is equal to the change in velocity is 32 meters per second divided by 4.5 meters per second squared, leaves us with a time equal to 7.1 seconds. So if you're going 115, it's going to take you about 7 seconds to come to a complete stop on average. And the 4.5 meters per second, it's just an average number that I took off Google. So it's going to depend on the vehicle a little bit and on road conditions and whatnot. But 7 seconds, 7 seconds, if you count that out, it's longer than you think. It can actually really make you stop and think about how much space you need to leave between vehicles. Example 5, similar type of question. You'll notice I'm using this 4.5 meters per second quite a bit. The average vehicle is capable of a maximum braking deceleration of 4.5 meters per second squared. In case you didn't remember from the last one. A collision results in a vehicle stopping suddenly. Okay, so it stops even faster than with brakes. We know what happens in those cases. If the vehicle is traveling at 16 meters per second, it's about 60 kilometers an hour in town, and comes to an abrupt stop in 1.2 seconds. So instead of our initial 7 seconds, we're now reducing our time to 1.2 seconds. How much greater is the deceleration than with normal braking? So I want to know, well, what's the acceleration if I stopped in 1.2 seconds compared to if it was just normal? So acceleration is equal to the change in velocity divided by time. Our change in speed, we're going from 16 to 0. So the change in speed equals 16. So 16 meters per second divided by a time of 1.2. The acceleration is equal to 13.3 meters per second squared. Now, that's a large acceleration. To put that in perspective, sometimes you'll hear people talking about how many G's of acceleration somebody experiences. I remember being at the air show, and there was an older gentleman who was flying a stunt plane, and at one point, I believe they said he had 12 G's of force on it. What that means is his acceleration was 12 times the acceleration of gravity, or the acceleration that an object would have just falling through the air. At that acceleration, you want to basically make sure your stomach's empty, make sure your bladder's empty, or where it depends, because all your fluids are pretty well gonna, it puts enough force on you, you're gonna empty your bladder and perhaps your stomach, and you may perspire a fair bit. Apparently after doing those stunts, their suits are pretty wet, and we won't say what all they're wet with. I'm assuming you'd have similar scenarios when you're driving really high-speed racetracks, as you have to watch for how many G's of force you experience when you're going around tight corners. Now, you're not going quite as fast as you are when you're in a plane. So 1 G of acceleration is 9.8 meters per second squared. This acceleration is much larger than that. So what that means is if you have a collision and you impact, and your acceleration is greater than that of gravity, it means the impact is going to be even harder than if you fell. Okay, so that's why oftentimes things hurt so much. And so it's almost 3 times 4.5. So if you take 4.5 divided, 13.3 divided by 4.5, you get roughly 3. It's almost 3 times larger than normal braking. So with normal braking, I don't sustain any injuries because the deceleration is small enough. I may feel tension from a seatbelt, but when you're stopping very suddenly, you have a sudden stop, that almost instantaneous stop during a collision, that large acceleration is going to result, we'll find in our next lesson, is going to result in a large force on my body, and that large force on my body is going to result in injury. So that's one of the reasons why cars are developed with safety features, to make this acceleration, the acceleration during an accident, as small as possible to reduce injury, or at least help minimize some of the injury that would happen if they didn't have a safety mechanism in place. The next question. The average vehicle is capable of a maximum braking deceleration of 4.5 meters per second. So we got the same number again. That's actually on the high end. What road conditions result in less stopping ability? If the deceleration on wet roads is reduced to 3.5 meters per second, so we've got wet brakes, we can't slow down quite as quickly. How much longer is it going to take to come to a stop from 30 meters per second on a wet day to a dry day? So first of all, well, let's figure out how long is it going to take to stop on a dry day. So acceleration is the change in velocity divided by time. So the time it takes to stop will be the change in velocity divided by the acceleration. So on a dry day, the time, our change in velocity, I'm going from 30, whoops, I'm going from 30 down to 0. I've just lost signal here on my tablet. I need to plug in. Okay, I've got a cord close by. We're good. We're saved. Just plug in here for a sec. It's been flashing, and I figured, oh, I'll take my chances and see if I can make it, but not so lucky. All right, so maybe you have this calculated by the time I finish plugging in. So on a dry day, the change in velocity, we're going from 30 meters per second to 0. We're coming to a stop. So the change in velocity is going to be equal to 30 for both scenarios. So 30, what's the acceleration on a dry day? Well, on a dry day, it's 4.5. How long does it take me to stop? About 6.7 seconds. What if it's wet? So on a wet day, same formula. The time is equal to the change in velocity divided by the acceleration. On a wet day, I'm going the same speed change. So 30 meters per second is my change in velocity, divided by, instead now I have less deceleration. I can't slow down as quick. So 3.5 meters per second gives me an gives me a stopping time of 8.6 seconds. You'll notice it takes almost 2 seconds longer to stop in wet road conditions than dry road conditions. And that leads us to my think and apply. Why is it advised to slow down during slippery road conditions? If your brakes can't grab as much and your ability to decelerate decreases, it means it takes more time to stop. Anytime acceleration drops, we're going to find that time it takes to stop increases. They're inversely proportional. Remember that from last semester? So the acceleration goes down, the time it takes to stop goes up. That can result in some really nasty consequences. So please, when you're driving, especially on these snowy days, make sure you leave lots of space between vehicles, because you know brakes don't work as well when they're wet. And if it's icy roads, there's not as much gripping ability on the road. It's going to take you more time to stop. Sometimes I've had vehicles behind me in poor weather, and I'm surprised at how closely they travel. And it's dangerous not only for you, but also for the vehicle in front, because if the vehicle in front stops quickly, you don't have enough space. You can injure them, and they can injure you. So it's something important to think about. The greater the speed you're traveling, the more space you should leave between cars. Why? Well, if I'm going fast, it's going to take me longer to stop because I need to change my speed more. So if I need to change my speed more, it takes longer to decelerate. If it takes me longer to slow down, my formula for speed says that my formula for speed says that the distance I travel is equal to the speed times time. So if my speed is higher and the time is longer, it's going to take me longer to stop. So I need to make sure there's enough space in between that I can come to a stop. The car has room to travel as it comes to a stop before I collide with somebody else. So just good reminders during winter weather to pay attention, be cautious of snowy weather conditions, leaving that extra space, and just being mindful of how physics impacts our everyday driving. If we're not thinking about it, we might not think about it as physics, but if you're not thinking about how slippery road conditions, the driving conditions impact your driving, you really should be, because that's part of being a defensive driver. I know some of you in the class are a little older. One of those spiels you may give your kids. But for some of you that are still considered young drivers, is something to be mindful of. I lost a student 1 year, so I'm always worried whenever I see a snowy day, even although I don't see you in class. I'm always worried about my students who are driving back and forth to school, wondering if they have to come in for class, because we like to see you get there safely and finish out your year safely. All right, so just a quick summary. If you haven't, hopefully you've got to this slide. Acceleration is the rate at which speed increases. Deceleration is the rate at which speed decreases. In order to calculate, it's the change of speed is equal to acceleration times time, or acceleration is the change of speed divided by time. So you can use your triangle. To find a final speed, if you're looking for the final speed, so a car has accelerated, you know what the change in speed is, and you want to find out, well, how fast are they going now? If they're accelerating, you're going to add it. If they're decelerating, you would subtract the change in speed. So one of those things to watch. So you're going to add or subtract the change in speed, depending on whether the velocity was increasing or decreasing. So that should give you enough to be able to work through a few practice questions. I know it's not something you'll calculate a whole lot of, but we'll split your questions. We'll half and half. You'll have about 5 questions with math, and then you'll have a few questions that just have some think and explain questions, okay? Just getting you to engage with the content and apply it in an everyday scenario.